we are recording. The first thing I'm going to do is make a little announcement because I got a surprise last Friday when I was hired to teach this course and to teach the modern physics course. I wasn't supposed to be here. I think we mentioned that at the beginning. It's because the professor who was supposed to be teaching this course, he's stuck in Europe right now. He works at CERN, the collider that's in Switzerland, and because of the COVID issues, he was not able to get his work visa to join the faculty. When I was added to that list of faculty in September, about a week and a half before the course started, the dean's office didn't add me to the email distribution list. And so I was never on several faculty emails, including the one that said that on the 5th of November, the day after the day after Election Day, we've got an advising day. And according to the registrar, no classes that day. Didn't know that. Wasn't on the email list. So here's what my plan is. And if anybody can't support these changes, you got till about the end of the day tomorrow to let me know. I mean, I can always go back to the plan as written. We cancel a day and you get one less physics lecture for the course of the semester. I could probably make that work. But if we're going to fit everything in, this is my plan. All right. And most people don't mind when you move an exam to a later date. And that's my proposal. Right now, the exam, let me share my screen with you right here so you can see what I'm looking at. I'm looking at my Google Chrome here, and I'll make it a little bit bigger. Hopefully you can see it. It's the one thing I can do this too. Hang on, I'll do the Command plus trick. There it is. And if you look in red right there, that's the exam this Friday. And my proposal would be move that to next Wednesday. It's a take home. And so I would distribute it. I would send it out on Canvas on Wednesday, and it would be due Thursday at the end of the day. Okay, so the exam then moves to next Wednesday, Thursday, and you can see there is no lab scheduled for next week anyway, and that's generally what I do in the vicinity of an exam. And then I would move the two topics that are for next Monday and Wednesday. They would slide back to this Friday and next Monday. Okay. All right, that's my plan. That's my proposal for you. That's what I'm going to be doing. I'll make a quick modification to this. It'd be switching around those three periods right there. But the exam, which is a take home, winds up being next Wednesday and Thursday. The people who have lab on Thursday, obviously you could see it as the exam is being given during your lab day. I do worry a little bit about the schedules of the people who have lab on Wednesday and of course class on Wednesday. You have to find somehow in your day Wednesday or Thursday, about an hour and a half, just like last time. Whatever it took you to take the last exam, that's how much time you have to have scheduled to do the exam next week. On the positive side, it gives you a couple more days to get ready. I'm not going to change the scope of the exam. It'll still be up through chapter 8. So the material we're doing right now on impulse, momentum, and collisions, all that sort of stuff, that's still reserved for the final exam. And so not changing the scope, just moving the date from Friday of this week till Wednesday of next week. You don't have to declare now if you have any objection. If you got an objection to that, please just send me an email sometime today or tomorrow. I got somebody in chat here. November 4th. Yes, I do mean November 4th, next Wednesday. And yeah, 5th is Thursday, isn't it? Election day is Thursday the 3rd. Yes, thank you. Yeah, thank you, Anna. That's I do mean the 4th. Scheduled as a reading day. I just didn't know it when I made this schedule up because the reading day was not in effect on the registrar's schedule. And I think we don't do all the Monday holidays, but we're taking all of Thanksgiving week off. And so I guess that's the payback, but they did stick back in the reading day on the 4th on next Wednesday as a day of no classes. And I didn't know that. Anyway, that's my proposal. If you have any issues with doing the exam next Wednesday and Thursday, as opposed to this Friday, please let me know. Enough on that. Let me put that away, stop sharing this, and got a bunch of questions for you today in our student polling here. Let me shift over to my PowerPoint and make this a little smaller so that your screen is a little bigger. And we're looking at interactions between two objects, collisions, if you will. Okay. Hopefully you've never been in an auto accident. You see, that's a kind of a violent thing where two objects collide. You can have the opposite, where two objects just push off each other. We're going to see that in the lab this week. And this was one of the examples I did last night in the pre-lecture video. And the point is, we talked about impulse and momentum on Friday. Okay, so an impulse, a force acting over some time interval, it changes the momentum. Well, what if there is no impulse? If there is no impulse, if there is no what we say external force, friction's a great example of an external force. And external force in the direction that things are moving. You know, there's always going to be gravity, right? There's always going to be a normal force on these two people, but there's no motion in the y direction. We only care about forces acting in the x direction. Well, if there is no external impulse in the x direction, that means the change in momentum is equal to zero, okay? And that means whatever the initial momentum is, that has to be equal to what the final momentum is. And you do have to remember that momentum is a vector. Okay, so you have to pay attention to directions. And in this particular example, when they push off of each other, this person is moving to the left. Generally, we make that negative. You don't have to. You can reverse what I'm about to say here. This person is moving to the right. We generally make that positive, and that's all we really need to do for vectors, right? Just to note positive or negative to tell whether they're going to the right or to the left. So this is the concept. And the reason we work with this is I got no idea what kind of force these two people are pushing on each other. And in PHY101, we're only really equipped mathematically to work with constant forces. Why is that? Well, because constant forces lead to accelerations, which are also constant. I should put a little s there, constant, not cont, C-O-S-T, okay? Because we have a set of equations that we can work with if we know what the acceleration is, and it's constant. We can figure out what the velocity is later. We can figure out what the position is later, okay? Well, I have no idea if this force these two people are pushing on each other is a constant. In fact, last week, we studied a category of forces, springs, and we showed that a spring was equal to, the force of a spring was equal to K times an X. And we usually put in a negative sign right there that I don't take too seriously, because all it means is the direction of the displacement. That's a delta. Let me write that a little neater for you. And then I'll make my point. The force of a spring was equal to minus, which just means that the displacement and the force are in opposite directions, K times the displacement. And you can see for different displacements, the spring force is going to have different values. It's not going to meet the requirement of a constant force. Okay, so that makes, although a very simple idea out of Hooke's law, it makes very complicated Newton's second law type problems if you try to put a spring in a problem. Okay, it's really hard to deal with, okay, because the force isn't constant, the acceleration therefore isn't constant, and none of our constant acceleration equations apply. So as an alternate technique, let's just look before and after the force is applied right here, where these two people are pushing off of each other. And if there are no other forces other than those two between the objects in the system, well, we can say there's no external force, there's no change in momentum, it has to stay the same. Now, remembering that momentum was just equal to the mass times the velocity, all conservation of momentum problems of this sort, where you don't know much about the force, but you want to know what happens right before or right after, you look and you go, okay, there is the momentum, and you got to subscript it with something. If you remember, this is S for Sandra here. So Sandra's momentum, and I think the other guy's name was David. This is David's momentum. And so we subscripted it with David, okay, with a D. Those momentum, and this person happens to like doing final first. I kind of, in my mind, like initial first, initial on the left, final on the right. Whoever made up this this equation, I guess it's one of our authors, Knight perhaps, liked going final then initial, but it's the momentum of Sandra final, momentum of David final, has to be equal to the momentum of Sandra initial plus the momentum of David initial, all vectors, okay? And in this case, you can see they start off at rest, so the initial momentum was 0. They're at rest, both of their velocities are 0, and that's often a simplification, which we like in problems. So this is it right here. Those are the big equations. They're really more concepts than equations, to my mind, okay? You have to look at something before an interaction, something after an interaction, and the thing we're hoping will stay unchanged. We say conserved then, conservation of mass, conservation of charge. Conservation of momentum is a fundamental physics principle. All it means is if there's no external forces acting on the object in a particular direction, the momentum before and after is the same. Okay, and you have to write something like this out. So if I was doing a problem, the first thing I might write to help myself get it right is that the initial momentum is equal to the final momentum. And then I'll go, okay, that means the momentum of Sandra at the end and the momentum of David at the end, that's an F right there, have to add up to be the momentum of Sandra initial, momentum of David initial. That would be step 2. And then I would substitute in what the momentum is from mass times velocity. And at this line, I'd be very careful about what's in what direction if I can figure that out. All right, and so that's the flow of these momentum problems, and we'll get a chance to do those here in a little bit. But first, I got some questions for you. Give you a chance. Any questions before we move on? That's it in a nutshell. All right, so let's move on to our first polling. I don't hear anybody, and I don't see anybody in chat, so we'll move on. Let's see, where does it start? Right about... Yep, hey, look, I hit it. All right, so the first one, and this is actually not a hypothetical problem. I built that apparatus. It's actually sitting right over there here in my office on a plank. I've got the track we always use, 2 carts, and see I've got this spring right in here, just the same sort of spring we talked about yesterday with a Hooke's law spring constant. It's compressed, and then this little thing right here latches it in place, okay? And then I have the ability to cut the latch. In our apparatus, I have a little button I push, which releases the latch. And then, of course, the spring applies a force to both of the carts, and they move that way. Okay, so that's the picture. And it says a piston. The way it does it is on one of the carts, it actually takes the spring, and when you push it, this piston right here, it compresses the spring. When I release the latch, it pushes that piston back out. Of course, the piston is what pushes on the other cart, not the spring directly. So it just makes a nice surface to apply a normal force. And so that's the meaning of the word piston. Okay, so out of these, which is true? And I guess it's time to find the right number here. 921, launch the poll. And I guess to say, yeah, equal mass carts, they are identical. And that's the key, I guess. All right, we're up to 23 today. '24 even. All right, somebody else joined us. All right, been going just about a minute here. I'll cut it off because it looks like the majority of the people get it. I'll share the results with you. Yeah, equal and opposite velocities, okay? And I guess the flow of the thought process, the reasoning that goes through this is the initial momentum, 0, right? Just like in those 2 figure skaters or whatever on the ice, okay? And so afterwards, the momentum has to add up to 0, but clearly this cart, I don't know, I'll call it the one on the right. Sometimes we subscript with things that help us describe what it is. That's fine. It's kind of your style in writing a problem. It's as if you're writing a paper and you've got characters in your paper. You can name them anything you want. Sometimes we'll go 1 and 2. Sometimes we'll go A and B. If you're deciding, you decide something that helps you remember. There's the one on the left going that way. Those momentums have to add up to 0. they have the same mass. And so the only way the momentum could be the same in magnitude but opposite direction is if they have the same velocity, right? And well, I would generally call this one negative and this one positive. But again, that's style. I can flip those around. They'll still add up to be zero, even if I flip those two signs around. So we're good to go. Yeah, so those of you that went C, exactly right. Next one. This one's a little subtle. Stop sharing that. That's a person on rollerblades. There's the ball. Yeah, most people seem to have it here. And they keep throwing it back and forth, I guess. At least twice to each other. So, bloop. And then this person has it, throws it back, and what happens? All right, we're up to 25 people and 23 in. I'm going to end it because most people seem to get this. For those of you that didn't see it, I guess the thing to remember is right here, when this person's holding the ball, initially the momentum is zero. If the person throws the ball that way, okay, so there's a momentum for the ball going that way. Well, that must mean that there's some momentum for that person that way. So the momentum of the ball is to the left. The momentum of the person then as they throw it must be to the right, okay, because there was zero momentum at the start. That's sort of how jet propulsion works, right? That's what we talked about in the production video. You know, we expel fuel and the rocket goes the opposite direction as the fuel is expelled. Even a jet engine on an airliner does exactly that. It just brings in air in the front very slowly, compresses it, shoots it out really fast out the back. The air goes out the back very fast. It pushes the airplane forward by conservation of momentum. All right, then the second step, so we already established now this person's moving that way and no external forces, no friction, continues to move with some velocity that way. When this person catches it, okay, well, the person's momentum was initially zero, but the ball had some momentum that way. The person holding the ball has to have some momentum that direction after they catch the ball. And so right away, after just one throw, they're continuing to separate from each other. As soon as this person catches it and throws back, the roles are reversed and they continue to move further apart. And so those of you that pick D, great reasoning. All right, moving on to the next one here. This is an interesting propulsion problem, I guess. Will this person move? Which way? Lot harder problem. A lot harder problem. Again, frictionless track, frictionless wheels are none of this work. So it's almost a how many angels can dance on the head of a pin sort of question, because I don't think you could ever really build this. All right, I think we got a majority and we got 23 people in. I'm going to show you the answer and share it with you. You know, I can live with A but the correct answer is B. Now, here's why. All right, right now, momentum is 0, right? The person's holding the ball. While the ball is here traveling towards the wall, I do agree that the person, and assuming the person brings the cart with them, the initial velocity will be that way by conservation of momentum. All right, but, and here's the but, there's one mass and one velocity's worth of momentum that has to be balanced up with the big mass of the cart, the man, this little wall here moving that way. Okay, now the ball hits the wall here, and the momentum initially was little m, the mass of the ball times the velocity, and then it rebounds back. It may lose a little bit velocity, but the change in the momentum here is that way, and it's approximately equal to twice the mass of the ball times the velocity of the ball. See, you've got twice the change right there. That gives us an impulse this way, which tends to move the ball. Now, you'll say, okay, well, initially he goes to the right, but as soon as the ball recoils off the wall here, starts to move to the left. And this force right here, because this change in momentum is bigger than this momentum right here, he'll initially go to the right until the ball recoils, and then he'll move to the left. Almost twice as big a change when the ball bounces off the wall than when the ball leaves the person's hand. And so that's the reason I would say after a couple of throws, and you can see he's got 3 more balls at his feet, he should be moving to the left. Initially, once the ball leaves his hand, I agree, he's going to the right. But once the ball hits the wall and bounces off, you get a bigger force to the left. All right, tough problem, but hopefully that made some sense. And but if you just continue considering the initial throw, I do agree with right, but once it bounces left, it's going to move though. It's going to move. They don't balance is, I guess, the point. And the reason is because you have a complete change in direction here, where here you just go from at rest to moving to the left. All right, let's see. We'll stop that one and we'll move on to 4. I have 8 problems today, by the way. Another one of those hypotheticals. Everybody gathers at one spot. I don't know, pick a country. Everybody in the entire world jumps up all at the same time. Imagine being able to do that.
Are we counting air resistance and or gravity?
The answer on air resistance is no. It's like friction, so no. And gravity, well, which gravity? Because there's a third law piece here, right? There's gravity on the people, and then the people's gravity pulls up on the earth. And that is why conservation momentum seems to work, doesn't it? You always have that equal opposite Newton's third law of force to think about. Good question, though, but no on air resistance. Let me draw the picture as I see it. There's the before. All those people are in this big ball right here. And there's the after. People going that way. And then I guess what happens to the earth with some momentum? That's momentum of people. All right, looks like that's the folks that are, everybody's in that normally is in, share the results right here. And yeah, I think the answer is, in principle, yes. Okay, while the people are all jumping in the air there, okay, the earth must have some momentum that's exactly the same value, but opposite in direction. Are you going to see the earth move? Well, no, because the mass of the earth is so big, the velocity that the earth must take on is imperceptible compared to its size and other motion. Okay, but in principle it does. And remember, this is what I was saying in response to the question, is if all these people were to experience a weight force, remember what we said is there's also a force of gravity of all the people pulling back up on the earth. Those are an action-reaction pair as defined by Newton's third law. They're equal in magnitude, opposite in direction, but the force of gravity of all the people pulling up on the earth is, again, inconsequential compared to the rest of the earth's motion. So it's not a force that could be measured. I will say one thing, though. If we're looking at the moon and the earth pulls with a force of gravity on the moon, okay, the moon does pull back with a force of gravity on the earth, and that we actually see. It's what manifests itself as the tides. It pulls on the water of the earth, and there's always a little bulge in the oceans, and I've greatly exaggerated it here. The water gets pulled in the direction of the moon, and that is the Newton's third law force of the moon pulling back on the earth. And that's why tides are basically daily, because as the earth rotates in one day, this bulge always stays facing towards the moon. All right, tides, currents from a guy who was at sea a lot. Stop sharing that. Move on to the next one. And so, yeah, this conservation of momentum is related to Newton's third law. Let's launch that and go on to the next one. This time we're not pushing apart. Now I've got two carts, I guess. Initial one has speed v going that way. And then that's the before, that's the initial picture. The after picture is two carts stuck together going that way. And I guess they have identical mass. Is that what it says here? Yeah, identical mass. So the two masses, we'll just call them M. And a lot of you got it right away. $16, we'll wait a few more here. All right, one or two more here. All right, here's the thought process. I'll share the results. The majority of you have it. Good work. Momentum of this guy, 0. Momentum of this guy, MV. And as I said, our textbook seems to like to think about final first, then initial. I like to think about initial first. So that term goes with that. The 0 goes with this guy. It's at rest, 0 velocity. After the two carts are together, so that's M plus M. Let's just call that 2M. And that's what we don't know. And so in all these conservation of momentum problems, momentum initial, the momentum final, there's got to be something you don't know. And in this problem, it's V here. You don't know the mass either, but notice it cancels. It's on both sides of the equation. And so this is V initial here, actually, I guess. This is V final. So I don't confuse myself. I should make a distinction there. That's V initial. And this is V final. And so V final, like most of you decided, is just whatever the initial velocity was over 2. The initial velocity was given as V. And so there you go, V over 2. There's the next one, and we'll go on to 6. Think about like a Yugo and a cement truck collide. Excuse me. All right, I'm going to end the misery here. Yeah, it's a subtle question. It is sort of related to that question I think I've said before, which weighs more, a ton of bricks or a ton of feathers? And the answer is they both weigh a ton, right? So I want you to look at the momentum initial here, and assuming no external forces, they just act on each other, the change in momentum is zero. Okay, so watch this logic. That means I don't know what to call the compact car because I got C here. I'm going to go, it's a Yugo because that's my favorite cheap little contact car. If anybody drives one, I apologize. So the momentum of the Yugo initially plus the momentum of the cement truck initially has to be equal to the momentum of the Yugo final plus the momentum of the cement truck final. If you believe that conservation momentum is true because there are no external forces, it's not a universal law. You have to first of all say, nope, there's nothing external. And of course, friction always will act, but it takes some time and some distance for friction to have an effect. So we throw that one out mostly in these analysis. It's sort of like if you have a pool cue ball hitting the 15 balls in the rack, initially momentum's conserved, but ultimately all the pool balls come to rest due to friction, right? But just before and just after the collision, very little effect for friction just because it hasn't had enough time and distance to act. And so we consider it negligibly small. Same thing here. All right, watch this as I just rearrange things. The momentum of the Yugo initial minus the momentum of the Yugo final, just brought this guy to the other side of the equation, has to be equal to the momentum of the cement truck final minus the momentum of the cement truck initial. I just brought that guy over to the other side of the equation. I think this would be minus the change in momentum of the Yugo, but notice that is the change in the momentum of the cement truck. The two changes in momentum are the same. And there's the rigorous proof, as rigorous as you can get here. Remember, change is always final minus initial. The Yugo, the way I set it up was initial minus final. So their change in momentum has to be the same, of course, opposite directions. If the Yugo is going this way, its change in momentum is to the left. If the truck is going that way, its change in momentum is to the right. And that's the meaning of this negative sign right here. All right. So same for both. C, that's the answer. And very few people got it. To the four of you, great thinking. You nailed it. All right, here is number 7. Two more to go. This one's a little numerical, but the numbers are easy. How fast is the 2-kilogram box going? And little collision, I like thinking about it as a little spring right in here, pushes the two apart. All right, looks like most everybody's got it here. And I'm going to end it because it looks like just about everybody's got it. I'll show you the answer. It is, of course, 2 meters per second, right? The momentum going this way is 4, actually probably minus 4 units of kilogram meter per second. Do keep units in here. It'll keep you from forgetting to divide through by something. And over here, you've got 2 kilograms times, of course, the unknown velocity. That's a kg. So in order to solve for that unknown velocity, you just take 4 divided by 2, and you get 2 meters per second. Here's one more. That's just the answer. There you go. Two boxes gliding along a frictionless surface. Same numbers again, right? What's their velocity after the collision? Yeah, most of you got it. All right, we go in a minute. I'll share the results. The majority see it, absolutely. You got 4 kilogram meters per second that way, 2 times 2. You also have 4 kilogram meters per second that way. You add those up, the initial momentum is equal to 0, isn't it? And so that has to be the final momentum after they hit and stick together. That must mean that once they hit and stick together, there's no velocity. C is the answer. Good work. All right, share the results. Majority of people got it right there. All right, hey, that's it for questions. There were quite a few of them today. I have 2 short problems for you to work on for the next, what do we got, 11 minutes before class is going, and I'll hang around afterwards. And there's also an extra credit. I just want to share that with you. So I'll stop that. I'll stop sharing this and show you the worksheet real quick. And so very similar problem. The numbers are a little harder. Okay, initially a person's on ice, they're at rest, he pushes, and then I guess somehow he twists himself around. So similar problem to what we just did there, only with real kind of numbers. Do that one real quick. And then very opposite, but like the last one we just did with, again, harder numbers. I got a 5 kilogram block moving 1 meter per second. I guess that's to the right. Hits block B, 3 kilogram sitting at rest, so velocity is 0. Perfectly inelastic, that's a term of art, means they stick together after the collision. Okay, and you'll see that in other problems. Okay, so that's the 2 problems to do, very similar to the last 2 we just did, only harder numbers. I do have an extra credit problem to work on if you want to give this a try. In this case, notice that they're going to collide right here in the middle, okay, right about there somewhere, but you have only an X component of momentum for mass A. If you look, mass B has an X and a Y component of momentum. The hint on how to solve this one is the momentum has to be conserved in both the X and the Y direction. So you actually work this problem twice if you want to give it a shot. All right, that's what I got. I'm going to break you up into 6 groups. I'll jump around for the next 5-10 minutes, give any hints I can give you. And this will, of course, be due on Monday, but you should be able to finish it up in 10 minutes that we've got left in class here. All right, we'll start, if I can find where you put breakout rooms. We'll go into 6 groups here, and I'll see you when I jump around.
Dr. DeCourcy.
Yeah.
So for number one,
yep.
I'm having trouble like starting the problem.
Okay, here's what I would do. Look at the equations up at the top here. Okay, and I'll share my screen with you. What's the initial momentum?
Is it 0 or is it like?
No, it's 0. You're exact. Your first instinct was correct there. Yeah, initial momentum is 0. They're both at rest, right? And yeah. So afterwards, which way the block goes? Say east or west here. Yeah, the block moves west, I guess. And so there's the momentum of the block, and the person. Why am I doing that? Feet. The person goes east is what they say. And you know the mass of the person is 59 kilograms, and you're given his velocity or her velocity 0.85 meters per second, right? So you know what the momentum is right there, product of those two things. The momentum of this thing must be equal, but in the opposite direction, such that the two momentums, the momentum of the person plus the momentum of the block after the collision, block, final, person, final, have to add up to be 0, right?
Okay.
That help? So multiply together and then divide through by the mass of the block. That should give you the speed of the block, shouldn't it?
Okay, thank you.
You bet. And don't forget the way it does ask, what's the velocity? Velocity does mean direction as well. So don't forget to either draw a picture like this. So I know you're going to the left. West is also correct in this problem. All right.
Okay, thank you.
You bet. Any questions here? Got the first one set up. Maybe got the first one done, actually. It's almost, if you understand how to do it, it's dead silent.
Is it negative 2.08?
I got 2.09, but yeah. And by negative, what do you mean? If the person is going to the east.
It's going to the west.
Yeah, you got it. Perfect. All right, I'll leave you guys alone. That was strange. I got kicked out of my own meeting. Had to re-get the internet. Any questions from you guys?
No.
Okay, you got an answer for the first one yet? Want to check your work here?
Okay. Oh, no, I do not.
All right, well, I'll be back.
Okay.
That was group 3. Let's go for 4. Any questions from anybody?
Not yet. I'm just starting number 2.
Okay, what answer did you get for number 1?
2.09.
Yeah, which way?
Okay. West.
West, perfect. Okay, so you got the first one. Keep going on a second. We'll see you in a bit.
Okay.
Uh-oh, I lost some people here. Any questions?
No,
All right.
I don't have any.
You get the first one right? Get it done yet?
Not yet. I'm still working on it.
Make sure you give a direction on the first one too. If the person gets pushed to the east, I guess that means the block gets pushed to the west, right? And that's part of the answer.
Okay, thank you.
You bet.
How would you set up the first one?
Yeah, sure. Here. What's the initial momentum?
Of the person, are we looking of the person or of the block?
I think the same for both, right? They're both sitting there at rest, right?
Isn't it 0 then?
Yeah, exactly. That's the key. The initial momentum is 0. And then the final momentum, well, it's the block times its velocity. And I guess that's final, isn't it? Plus the person, mass of the person times the person's velocity, final. And the problem gives you that, those two things, and it gives you that, right? And you don't know that, but you do know that the final and the initial have to be the same. So that all has to be equal to 0, right?
Okay. Yeah.
That's the setup. Yeah. Yeah. Okay.
Thank you.
And I guess in order for these two things to add up to be 0, one of them has to be negative. Usually it's the one going to the left. And that's the way the picture is. So I would probably make that one negative and that one positive. But if you see you're gonna solve for this velocity is going to turn out to be negative, isn't it? As soon as you bring that over to the other side of the equation, it becomes minus, and then you divide through by the mass, it stays minus. All right. Last room.
The initial momentum for both the man and the block. And then I put the mass of the man and the man's velocity in, and then the mass of the block times the final velocity of the block.
What'd you get for a number?
And then I got 0, which was.
I'm sorry, I missed the number. What'd you get for a number?
My final velocity was negative 2.09.
Perfect. Sorry, I didn't get to you guys till the end. You're the last group. That's exactly right. And you described it exactly how I would have said. Okay. You took the momentum of the person, its mass times its velocity, and you divide it through by the mass of the block, and that gives you the velocity of the block. All right. Hey, I'm gonna end the breakout rooms. We'll close them all, and we'll see you back in the main room. All right, I think just about everybody's back. I got 21 people back. Just want to remind you, moving the exam from Friday of this week to Wednesday, Thursday of next week. And if you have any objection to that, please send me an email sometime today or tomorrow. I can always put it back to the original schedule. But if I don't hear from anybody, that's the way we're going to go. I'm going to hang around for office hours after class here, and then I'll be back for office hours again at 10:30 for those of you that have to go off to class. Have a great day.
Thank you.
You bet.
Thank you.